Today we will continue the topic, the title of foundation design. So this is the course outline. So for this foundation design, we will discuss on how to design of the combined footing, and then how to design of strip footing, rough foundation, pile, and pile cap. This is the general principle for the foundation design. Okay, for the category 1, small and simple structure, for example, the one-story building, and then all the building component, for example foundation, and also for the upper structure will be designed by the structural engineer itself. No need to involve any geotechnical engineer on this project. That can be categorized as category 1. Okay, for the category 2, with the conventional with no difficult ground or loading condition, for example for the high-rise building or mid-rise building, but the soil condition is easy to handle, easy to estimate, easy to calculate for the bearing capacity. So for this category can be done either by structural engineer or by geotechnical engineer. But for category 3, for example, the other types of building with high risk of the geotechnical failure. For example, when you build a building near to the slope, so means you need to check for the slope stability. And also, for example, you want to build the building with the thick clay underneath of the building, so you need to check all the settlement of the soil under the building. So this can be done by geotechnical engineer. Okay, so in this slide you can see the safety factor for foundation design. For example, for permanent action, as combination 1, structure and geotechnical effect to the foundation design. So for unfavorable, we'll use 1.35 for the permanent action, and then for variable action we have 1.5. Okay, and then for combination 2, for consideration of structural or geotechnical failure, okay, we use the for permanent action. For unfavorable we have 1, and variable action is 1.3. Okay, but for the equilibrium checking, okay, we use this permanent action is 1.1, and then the variation is 1.5. So the accompanying variable action, for example, if you have the wind load, so you can categorize as the accompanying variable action. Okay, for partial safety factors applied to geotechnical material properties. Okay, so for example, for the combination 1, the angle of shearing resistance gamma pi is 1, and then for the effective cohesion is 1, and then strength is 1, and confined strength is 1, and bulk density is 1. For combination 2 is for the angle of shearing resistance 1.25, effective cohesion 1.25, and then strength is 1.4, and confined strength is 1.4, and bulk density is 1. So there are 3 alternatives for simple foundation design. First, by using the direct method, where calculations are required for each limit state using the partial factor of safety for action and material properties as appropriate. And then the second is the indirect method, which allows for simultaneous blending of ultimate limit state and serviceability limit state procedure. And then the prescriptive method, where an assumed self-bearing pressure is used to size the foundation based on the serviceability limit state, followed by detailed structure design based on the ultimate. Based on these 3 alternatives, so we select the prescriptive method because the method also has been used previously during the RC design 1 when you design for pad footing. So where we need to determine the dimension of the foundation by using the serviceability limit state loading. And then when we design for reinforcement we need to use the ultimate limit state UL. Okay, so in this slide you can see the typical allowable bearing values. So this the rock or soil, actually the type of the soil, and then the right column is the typical bearing value in kilonewton per square meter. Okay, in practice we call as the kilopascal, kPa. So for example, the massive igneous bedrock have the 10,000 kPa. Okay, sandstone 2,000 to 4,000, shales and mudstone 600 to 2,000, gravel, sand and then compact medium dense sand from 100 to 300, and then loose fine sand less than 100, very stiff clay 300 to 600, stiff clay 150, firm clay 75, and soft clay is less than 75. Okay, so normally we will use the when we design for foundation, we need to put our foundation at the very stiff clay, or we can socket at the rock. Okay, depend on the decision of from the engineer. The problem is if we have the thick layer of the soft clay under our building. So because the soft clay, the capacity or the typical bearing value only 75 kilonewton per square meter, so we need to do some treatment on the soft clay. Okay, or maybe we can use the deep foundation, so the end of the pile will be socket direct to the rock. Okay, so no contribution from this soft clay. Okay, so this is the combined footing. So we have here the two figure here. The left side is for the rectangular combined footing, and then the right side is trapezoidal combined footing. So how to decide whether we need to design as rectangular trapezoidal? First, depend on the value of loading acting to the column, and also depend on the uh, what you call the shape of the your length for the building. So if your length no constraint on the length, people will use the rectangular. But for example, if the location of this foundation at the border to the other people land, so no choice, we need to have the pattern of the foundation based on the border line. Okay, on the border line. Okay, so where two columns are close together, it is sometimes necessary or convenient to combine the footing to form a continuous base. So actually, when you design for if this the left column and the right column, if you design separately, they will have the overlapping between the foundation from the column, the smaller column and the bigger column. So better we can combine them in order to support the load together. Okay. The dimension of the footing should be chosen so that the resultant load pass through the centroid of the base area. Okay. The centroid of the base area. So between these two columns, okay, this may be assumed to give a uniform bearing pressure under the footing and help to prevent differential settlement. So when you design for the foundation, we need to reduce even to we need to prevent different settlement between these two columns.